Hi students, in this video I'm going to do a quick review of the special triangle. So that's the 45-45-90 triangle and the 30-60-90 triangle. It might be new for some of you, so I'll go quite slowly here. So the 45-45-90 triangle, or in radians, the pi over 4, pi over 4, pi over 2 triangle, is a right triangle and it's isosceles. So these two angles are each 45 degrees, which, as we know, equals pi over 4 radians. Now, this particular triangle has a special relationship among its side lengths. Because it's isosceles, each of these side lengths are the same, so we can call them each x. Then, the hypotenuse we can always get by using Pythagorean theorem, so we can solve for this last side by saying, let's call it c. C squared equals a squared plus b squared, which in this case is x squared plus x squared. So c squared equals 2x squared. So if we take the square root of both sides, we get that c equals x times root 2. Because I can pull the x squared out and make it just an x. So this is x root 2. So one example of a 45-45-90 triangle might have side lengths of 1 and 1, and then the hypotenuse would be root 2. So now if I'm trying to figure out the cosine, sine, and tangent of such a triangle, well, if I want cosine of pi over 4, I can look at one of these, and I'll take the adjacent side over the hypotenuse. So that will give me x divided by x root 2. And it doesn't matter what x is, I'm always going to have these relationships among the sides of my triangle if it's a 45-45-90. So the cosine of pi over 4 is always going to be 1 over root 2 because these x's will cancel. And if I rationalize by multiplying top and bottom of this by root 2, that's the same as root 2 over 2. So the cosine of pi over 4 is root 2 over 2. The sine of pi over 4 is going to be the opposite side over the adjacent. And so I end up with the same thing. I end up with 1 over root 2, which we just showed is the same as root 2 over 2. So sine of pi over 4 is root 2 over 2. The tangent of pi over 4 is the opposite over the adjacent, so it's just 1 over 1, which equals 1. So no matter what x is, because it ends up canceling out, if we have a 45-45-90 triangle, the cosine is root 2 over 2, the sine is root 2 over 2, and the tangent is 1. So now let's do the same for our other special triangle, the 30-60-90. Or the pi over 6, pi over 3, pi over 2. So my smallest is going to be the 30, or the pi over 6 angle. The next one, the middle one, is going to be the 60, or the pi over 3 angle. And the last, the biggest, is the 90-degree one. These also satisfy a special relationship. So if I have that the side opposite the smallest, so opposite the pi over 6 is x, then the hypotenuse is 2x, and the side opposite the pi over 3 is x times the square root of 3. This is only true if the angle measures are pi over 3, pi over 6, and pi over 2, or 30-60-90. So what does this say when I'm calculating the cosine, sine, and tangent for, let's say, the angle pi over 6? Well, the cosine of pi over 6 is going to be the adjacent side divided by the hypotenuse. So again, notice that the x's cancel, so cosine of pi over 6 is going to be root 3 over 2, no matter what the side lengths of our 30-60-90 triangle are. Similarly, we can do sine of pi over 6. That will be the opposite over the hypotenuse. So we get x over 2x. And the x's will cancel, so sine of pi over 6 is just 1/2. Tangent of pi over 6 is the opposite over the adjacent, so it will be x over x root 3. And the x's cancel, so I get 1 over root 3. If I do this same rationalization trick, that's the same as root 3 over 3. So cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. Tan of pi over 6 is root 3 over 3. We can do the same to find cosine, sine, and tan of pi over 3. So if I start here, the cosine is the adjacent over the hypotenuse. So I get x over 2x. The x's cancel, and this simplifies to 1/2. Sine of pi over 3 will be the opposite over the hypotenuse. So it's x square root 3 over 2x. The x's cancel, and I get root 3 over 2. And tan of pi over 3 is the opposite over the adjacent. So x root 3 over x, the x's cancel, and I just get root 3. So there's a little bit of a trick to remembering this that I'd like to show you. So let's look at the unit circle. Separated into quadrants. So if I want to study the first quadrant of the unit circle, I have a few special angles here. So this one is pi over 4. That line represents pi over 4. Then if I separate this first quadrant into thirds, then this is pi over 6, and this one's pi over 3. So if I want to know the cosine and sine of each of these angles, what I can do is think about cosine and sine as coordinates. So the first coordinate will give me the cosine of pi over 6, and the second will give me the sine of pi over 6. So this one will be cosine of pi over 4, and this one will be sine of pi over 4. And similarly, if I write the coordinates for this point, I'll have cosine of pi over 3 and sine of pi over 3 are my two coordinates. Now, this is where the trick comes in. So, I'm trying to come up with a trick that's going to help me remember that cosine of pi over 3 is 1/2. Sine of pi over 3 is root 3 over 2, and cosine of pi over 6 is root 3 over 2, sine of pi over 6 is 1/2, cosine of pi over 4 is this, sine of pi over 4 is that. So what can I do? Here's the trick. If I set myself up this way, then I write the numbers 1, 2, 3, and then 3, 2, and 1. Now, what I'll do is take the square root of everything in sight and divide by 2 everywhere. One half is the cosine of pi over 3. We showed that here. Root 2 over 2 is the cosine of pi over 4. Root 3 over 2 is the cosine of pi over 6. Root 3 over 2 is the sine of pi over 3. Root 2 over 2 is the sine of pi over 4. And 1/2 is the sine of pi over 6. So again, the trick is label your angles correctly. Pi over 3, pi over 4, pi over 6. Then write 1, 2, 3 in the x column, 3, 2, 1 in the y. Take square roots of everything in sight, then divide everything by 2. The left column will give you your cosines in order. The right column will give you your sines in order. So I hope that this trick helps you to remember, but if not, you can always return to the special relationships among the angles in a special triangle.